The first thing is we're going to study about when resistors are connected in series. Now, what is going to be the consequence? What is going to happen? So, resistors in series. Resistors in series. When resistors are connected in series, what does it mean? You are actually having you're having a resistance, say R1, connected to a resistance R2, connect to a resistance, say R3, and all these are connected to a certain power source right there, and that is, so we have a power source, a potential difference of V volts connected across three resistors that are one after the other. So a connection like this is what we call a series circuit. If you don't understand anything, ask. Resistors in series simply means they are connected one after the other. Now, how do you, again, visualize it? Think of three roads. This is the traffic that is going this way. So let's say the traffic is this, right? Let's say there are 50 cars going this way. This is the first road, and then comes the next road, then comes the next road. So if the roads are like one after the other, then 50 cars will go here, and all the 50 will have to go here, and all the 50 will have to go here, right? Or think of them as three bridges. Then all the cars have to cross this bridge and that bridge. So you can look at it in different manners, like bridges. What you understand from here is that the current is the same throughout. The current here and the current here and the current here, they're all the same, and the current in the circuit will stay the same. So in all series circuits, what is common? Current is common, right? Now let's look at it with a different analogy. Think of these as three racetracks. You have racetrack number one, turf. The next racetrack is a sand racetrack made of sand, and this one is wet clay. So look at them as three obstacles: an easy track, sand track, wet clay track. Now, when students are released from here, how many students decide to go through the race depends on what factor? Depends on not just looking at the easiest path. How many decide to go depends on an overview of the entire race, right? Like, for example, if someone says, oh, we're going to have a race, you want to run? You won't say, yeah, I want. You want to know whether this is 50K or 10K. You want to know that part. You don't want to take a decision. The decision whether to run or not depends on the number. Like, for example, your first race is the 1K from here to there, and then the next part of the race is a 20K from there to there. So people won't take a decision of running by just looking at the first 1K. They'll say, all right, after the 1K, what comes next? And after that, okay, I quit. I don't want to go. So they want to know everything. They want to know everything, and then the numbers decided. So this current does not take a value by looking at only one resistor. It looks at the whole thing and says, okay. But if some decide to run, let's say 10 of them decide to run, all the 10 will go through here, then all the 10 will go through here, and all the 10 will have to go through there. There's no way back. Keep going. All will have to run through the entire hurdle, right? And now let me ask you this. Through which racetrack will they lose most of the energy?
Same.
Third.
The third one, the wet clay, is definitely a hard path to go. That is definitely a hard one. This is not as hard. This is pretty easy, right? So there they lose most energy. Here they lose some, but here they should lose a little bit. So the energy that is lost depends on the resistance. That is Ohm's law. V is proportional to R. Right? For the same current, V and R will go together. V is proportional to R. In other words, when you're told to run, you won't run through this easy track putting in 100% of your energy, will you? Will you run the first, like if you're supposed to run 50 miles, will you run the first 100 meters like Usain Bolt?
No.
No, you'll conserve energy, right? You'll just basically be jogging from here because you need to keep the energy for the whole journey. So what will happen is you will actually be taking this place, let it snow. What is that?
His computer was like, oh, someone turned on their mirror.
Okay, come on. So the running from here to here is not going to be in such a manner that you lose all the 100% energy. You don't run like that, losing all the energy here, because you'll always, okay, I need to run through this, this, and this, so you conserve your energy. So you lose some here, and then finally the rest of it here, right? A proper race that is properly run. So if you have a race that is run from point A to point B, the race must be run in such a way that you have 100% energy before the race and 0% energy after the race. That's the proper race running. If you have put in your 100%, you should not be able to stand on your legs at the end because you have zero energy. That's why people collapse. If they really put in their 100%, after the race, they won't have stamina to stand on their legs. They just collapse and fall. Some of them pass out. Now, if you're actually kind of planning on completing the race and waving to everybody, that means you're saving energy there. That means you didn't put 100%. So if you put 100%, that's your maximum. So generally, you keep a tiny bit of it so that you come and you're able to apply brakes and stop without fainting. Anyway, coming back to this. So not everything is lost here. You lose some here. So that's exactly what we mean by potential difference. So the potential difference is basically the amount of work that needs to be done to cross from here to here. Is that the same as here? No, that's a different one. So you lose a potential difference here, and you lose some potential energy here. You lose some energy here. Now why I'm putting plus minus on either side, plus implies you have more energy before the race than after the race. So there's an energy difference, right? I put a plus sign here implying for this resistor, this side is higher potential and that side is lower potential. For this one, this is higher and that is lower. This division of energy takes place in such a way, that the total is taken care of. So V is equal to V1 plus V2 plus V3. Like for example, if you have 100% energy here, you lose say 10% here, and then 30% here, and then 60% here. So you split it up that way. Depends on the difficulty levels, right? So you lose 10%, 30%, and 60% completes 100%. The rest of it, yes.
So is that diagram assuming that all the three different resistances are equal?
No, that's why I said they're all different. Okay. That's why I said this is only requiring 10 volts energy difference, 30 volts, 60. So
if
total is 100.
If they were all the same amount of
then you will have to spend equal energy. Perfect. Good question. So if they were all exactly the same tracks, then you'll just divide them exactly, proportionally, right? Proportional division. So that's the potential energy difference. So what is V equal to V1 plus V2 plus V3? Now, why is V1 there? Because the current is flowing through it. That's why V1 is there. What is V1 according to Ohm's law? What is V1 in terms of R1? IR1. And what is V2? And V3. Such that I can be taken common. So you have R1 plus R2 plus R3. Now if I divide throughout by I, you get this. Take notes very quickly. So if I divide through by I get V over I is R1 plus R2 plus R3. And what is V over I? What is this divided by this supposed to be? It's supposed to be R, right? And what is that R? That is the resistance offered by all of them together. We call it R equivalent. R equivalent means like one track. This is one track that can replace all the three tracks and yet pose the same difficulty. You understand that? So instead of three different tracks, can I just have one track which will create the same number of people run through it? That is called R equivalent. So what is R equivalent? That is here, R equivalent. So what you can see from here is the R equivalent is equal to R1 plus R2 plus R3 plus R4 plus R5. On the diagram, I'm just showing only 3 resistors, but you can apply to any number of resistors. So if you have a bunch of resistors in series, then the R equivalent is R1 plus R2 plus R3 plus R4. Just keep adding them up. Understood this? Now, what is about resistors in parallel? Resistors in parallel. When you connect resistors in parallel, how do they look like? These are resistors in parallel. R1, R2, R3. Those are resistors in So when you connect resistors in parallel, you have potential difference applied to R1, R2, R3. You can have any number. Now, so what do you understand about parallel connection is that if there is a current that's flowing here, if a current flows from there, watch what happens to the current. The current comes here, it comes to the junction, and then, so let's say there are students running from here. Let's say students are running from here, and this is the easy track, this is the sand track, and this is the wet clay track. What will happen to the students when they come here to the junction? Will all of them go through the easy track? Most people, yes. Most will go there. But looking at the congestion over there, some will say, all right, that seems to be crowded. I think I'll run on the sand track because hardly anybody is using it. So some will run here. And some will say like, okay, I know the wet clay is pretty hard, but there's hardly anybody. I can just leap across and go. We actually split up. When it comes to the junction, the splitting takes place. And the splitting takes place, most will go there, some will go here, some will go here. You get it? Think of it as roads now. See, I'm switching between examples. Think of it as roads. Imagine you're going on one road here, and then you come to this junction where there are 3 routes to go to the other side. We do this, right? We don't just go through the easiest track always. Like, imagine everyone wants to go from here to a certain spot. Okay? Everyone wants to go from here to a certain spot. Not everybody is going to travel through the same road, because then it will cause a lot of congestion. So automatically what will happen is some people will say, I know this is the shortest way to go, like half a mile, but you know what, since everyone is going there, it's congested. I know this is actually 1 mile, but I can go faster there because less traffic, right? So you do take the 1 mile distance because you know you can reach there earlier. Don't we do that? We take the slightly different route because we can reach there. Now, if you're going to be stuck on the half mile thing, you may be stopping and going all the way. So you'll take more time. and spend more gas. So you may save gas also there because you're just finishing the journey in a short time. You're going faster. There are differences. So that's what we do on the GPS, right? When you plug in the GPS from this point, the GPS tells you, okay, if you go this way, it's the shortest distance, but you'll reach taking a little extra time. This is a little extra distance, but you reach there earlier. So you do choose between the two, right? If you're not really time conscious, then you'll choose the distance-wise, vice versa. So that's exactly what happens here. Yes?
Going back to like resistors in a series, is R3 and R2, do they have greater resistance just because you said they'll give you like greater values, or is it because they're farther down?
No. R3 can be here, can be anywhere.
Okay, so like R1 could have the highest resistance.
Yeah. It can be anything. So I can actually have this one as the wet clay, and this one as the sand, and this one as a good track. In that case, what will happen is you will spend most of your energy here, a little bit less here, and the least for the last part. The division of energy takes place according to how much is needed to cross. The same way here. How many go through this easy track? How many go through this difficult track? It is decided by an overall energy conservation. It is decided by energy conservation. Let me give an example. Imagine there are 100 students running here. Imagine 100 students running here. And when they come to this junction, let's say 60 students are running through this junction, this place. And 30 of them are running through here, and 10 of them running through here. Now the 60 of them are running through here, and this is an easy track, so they won't spend much energy, right? So let's say they spend 100 joules to cross that. Let's say they spent 100 joules to cross that. How many joules altogether for all the 60? 6,000, right? 6,000 joules altogether. Now the ones who are running here are running through a difficult path. Each one is going to lose 200 joules. So how much is the total loss? 600. And this is a tough task. That's why only few are running here. But each one loses 600 joules. So what's the total energy loss? 6,000. So basically, the splitting up will take place depending on the total energy to cross. That's how they decide. The total energy to cross, that should be conserved. That means the potential difference from here to here is the same as the potential difference from here to here, the same as the potential difference from here to here. Make sense? Yeah.
Will that always be the case?
Always. Whenever you have parallel connections, the energy from here to here should be the same as here and same as here, because there are 3 parallel routes, no difference between them. So the splitting up of 60, 30, 10 takes place in that same proportion. Get it? So what you understand from here is that the currents will split up, but the potential difference is the same everywhere. It's the same as what you applied. It's the same as what you applied. What's the potential difference from here to here that you have applied? V. And it's going to be the same thing. Now, of course, you can't look at it with the numbers. It will make less sense that way. But that is what is totally available across these 2 points, and they split according to that. So in parallel, this is what happens. Each one gets the same potential difference. See, all the light bulbs here, they're connected in parallel. Each and every light bulb, this light bulb gets 110 volts. Next light bulb gets 110 volts. Next one, 100. They're all in parallel. Everything in this room, all television, everything is connected in parallel. So if one of them fails to work, like that one, if one of them fails to work, one bulb is out. Rest are not affected because each one is getting equal share, right? Each one is getting the 110 volts. So if something happens like that, only that is out, but all others are fine, not affected. Yeah.
Is that how modern Christmas lights work?
Oh, Christmas lights are series connections. Christmas lights are series connections. Now, modern Christmas lights, some of them use LEDs, which don't fail like that easily. So yes, they do have Series connect. Yeah, I mean they are mostly kind of parallel effect. Yeah, because they have lines running and then they just kind of branch it out. But not all of them. Some of them have sections of parallel connections, but those sections are in series. Now this one is a series thing. Let's say this is one light bulb, and if this light bulb fails, it's like this bridge is fine, this bridge is broken, and this bridge is fine. What do you think is the number of people running? 0. That means no current in the circuit. Because you look at the entire thing and say, oh, that's broken. I cannot run through that. So you decide not to run. You don't start running because the first bridge is fine. Make sense? So in series, the current is decided by looking at the overall thing. So if this is broken, the entire thing is out. So that's why in Christmas lights, if one bulb is gone, the whole segment is out. It's pretty tough to find out which one is out. Whereas in parallel, if one is out, only one is out. The rest is getting the same share. 110 volts connected to all of them. So each one is getting its share. Okay. So do you understand about parallel connection properly? Good. Now, what do you understand over here is potential difference is common, but currents are different. So I1 plus I2 plus I3 must equal to I. I1 plus I2 plus I3 should be equal to I. Whereas here, V1 plus V2 plus V3 should be equal to V. What is common over here through all of them? I. What is common over here through all of them? Voltage. You see it? You can write that next to it. Right here you can say I is common. V is different. And you can write here V is common, but I's are different. In parallel, V's are common, but I's are different. In series, I's are common, but V's are different. Now looking at this, what is I1 in terms of V and R? What is I1 in terms of V and R1? Say it again. V over R1. Therefore it's V over R2 plus V over R3. And you can see that I can take V common out. 1 over R1 plus 1 over R2 plus 1 over R3. Now if I divide throughout by V, I get I over V is equal to 1 over R1 plus 1 over R2 plus 1 over R3. What is I over V? V over I is R. What is I over V?
1 over R.
1 over R. So this is 1 over R equivalent. What is the meaning of equivalence again? What is one resistor? What is one resistor that takes the entire thing and substitutes it? So what is one resistance that can just substitute for all the three? What is one track that you can put between these two, which will pose the same difficulty that is posed by all of them? That is called the equivalent resistance. So we have 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and then if you generalize it, it keeps going. So you can see the equations for series. What do? Just add them all up. In parallel, you add all the reciprocals, and that will be this. Yes.
Is adding all the reciprocals not just the same as adding them?
That's a very common algebraic misconception. So try simple numbers. What is 1 over 2 plus 1 over 2? Is it the same as 2 over 4? Or 2? What is it? Is it the same as, like, this is 1, right? Basically 1 over 1. So 1 over 2 plus 1 over 2 is 1 over 1, right? So can I just say, oh, because it's all the reciprocals, 2 plus 2 is 1. No? So don't do that. R1 plus R2 plus R3 is not, it's not good. That's a very common misconception in algebra. If it is a product, yeah. If it is multiplied, yes, it's right. But if it is additions or subtractions, you can't do it. Alright, so you understand the equations for series and you understand the equations for parallel, which is the sum of the reciprocals will be equal to the reciprocal of the equivalent resistance. Got it? Special case. Only for two resistors in parallel. A special case only for two resistors in parallel. So suppose you have two resistors in parallel like that. Only for two resistors. What is the equivalent resistance? 1 over R equivalent is equal to 1 over R1 plus 1 over R2. Right? Only for two resistors. You can do it by taking the LCM. You can do it by LCM or whatever method. Or just multiply the whole equation with R1, R2. Product of R1, R2. Just multiply it. So R1, R2 over R equivalent is equal to R1, R2 over R1 plus R1, R2 over R2. I'm just multiplying throughout by R1, R2 because it's the least common multiple of these two. So what happens here? So what do you have here? R1, R2 over R equivalent is equal to R1 plus R2 or R2 plus R1. So what is R equivalent? If R1 or R2 over R equivalent is R1 plus R2. R1, R2 over R1 plus R2. So if you have just two resistors in parallel, it's easy to find the answer because all you do is product over sum. Product over sum. So that makes it faster to do the problem. You get it? So R equivalent is going to be just product over sum. I'm just giving this example. Let's say this one is 12 ohms and you connect 4 ohms in parallel to it. What is the R equivalent for this? 3. So what do? Product over sum. So instead of doing 1 over 12 plus 1 over 4 equals to 1 over R equivalent and working it out that way, this is faster. 12 times 4, which is 48, over 12 plus 4, which is 16. So 48 over 16 is 3. So the answer is 3. So this is applied only for two resistors only. So if you have 3 like this, if you have 3 resistors, then you have the option of doing 1 over 12 plus 1 over 4 plus 1 over 6 is equal to 1 over R equivalent. You plug everything into the calculator and then get the answer. That's one option. The other option is take 2 at a time. Like this, these two together, what's the answer? 3. So just imagine that you raise the whole thing and put 3 instead. Isn't the 3 and the 6 in parallel also?
Yeah.
So what is 3 times 6 over 3 plus 6?
2.
That's the answer. So if you can do by installments, you can do that. You understand what I'm saying? So if you have 3, you can do these two first and then combine that with the next one with the same rule. It's easier to finish. So product over sum of these two things will give you 3. And then that 3 and that 6 also are in parallel. So 3 times 6 over 3 plus 6 answer is 2. Or you can do 1 over R equivalent is equal to 1 over 12 plus 1 over 4 plus 1 over 3, no, 1 over 6. And then you get the answer. But the very common mistake what students do is they plug in this and this and this in the calculator properly and they enter and they forget that that is 1 over R equivalent. You have to flip it. Right? And the other thing I recently discovered is that students have no idea about a button on the calculator that will flip your answer for you. Yeah. There's a button very prominently sitting on the calculator. It says x to the power of minus 1. And you don't use it. Where is it? It's very clear. X to the power of minus 1. X to the power of minus 1.
It's under math.
So if you want to flip an answer, all you do is just press x to the power of minus 1 answer. That's it. Show me the calculator. So if I want to do, yeah, you go. So if I want to do this particular problem, I don't know if this, okay, so if I want to do this problem, I'll do bracket 1 divided by 12, close bracket, put that away, plus, who's this?
It's outside.
Over 12 plus open brackets 1 over, what is that, 4, close bracket, plus open brackets 1 over 6, close bracket, enter. So I'm getting an answer here, and then I know that that is 1 over R equivalent. Press the x minus 1 button and enter, and that is your final answer. So if I have 10 resistors in parallel, that will be easier, right? If you have 10 resistors in parallel like this, then doing 2 by 2 will be a headache. So the best thing is to do it that way. But if there are just 2 resistors or maximum 3, you can just do it by taking it in installments. Any questions here? Okay. Now when you put all this information together while solving problems, that's where we will see the difference. If you really picked up all this information or not. For identical resistors in series. For identical resistors in series. What do you mean by that? You have R, 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 N of them. You have identical resistors in series. So how do you find the equivalent resistance? R equivalent is R plus R plus R plus N of them. What is it? If you add R n times, what do you get?
In R.
NR. Say for example, if I have 100 ohms resistors, 20 of them in series, what is R equivalent? 2000. So I have 100 ohms resistors, 20 of them one after the other. So it's like 20 times 100, which is 2000. Right? So 100 ohms resistors, 20 of them in series will be like 20 times 100. Now, for identical resistors in parallel. So if I'm going to connect R, 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 it's a ladder of identical resistors. So if I have a ladder of identical resistors like this, if I have a ladder of identical resistors, how do you write it? 1 over R equivalent is equal to 1 over r plus 1 over r plus 1 over r goes on n terms. What is that going to be? 1 over r equal? Yes?
And 1 over r.
Yeah, n over r. That's right. N over r, because there are n of them. So therefore R equivalent is equal to R over N. So when you have identical resistors connected in parallel, you take one of them and divide it by the number. Say for example, if I have 100 ohms, 100 ohms, 100 ohms, 100 ohms connected all in parallel, and there are 20 of them, what is the equivalent resistance of all of them? 5. Because there are 100 ohms resistors connected, 20 of them in parallel, so the equivalent resistance is going to be just 100 divided by 20 is 5 ohms. So you don't have to do sitting down and calculating all those things again. If there are identical resistors, easy. So in a Christmas lights, the light bulbs are all identical resistors. So to figure out how much is the resistance of 20 bulbs, should be easy, right? Because they're identical. If they're different, then only you have issues. That's in series though. Christmas lights in series. And if I want to do the same thing for these, what is the equivalent resistance of all of these bulbs connected in parallel? Then I have to do this. Any questions? Yeah. Now let's see if you can apply all this information when you attack problems. Okay. So let me give you a problem to start with first. So if you have the power supply, three ohms, 7 ohms, all right. Now if you look at this circuit, and if I ask you, what is the current that's going to flow out of the battery? What is that current that's supposed to flow out of the battery? So as I said earlier, will the current just start flowing by looking at the 3 ohms? No, it will look at what? Everything. Which means what? Equivalent resistance of the entire circuit. So what is the equivalent resistance of the... So in other words, if I have to raise this, and all of them, what is one resistance I can put instead of all of these? That's called equivalent resistance. Find that out. Once you know the equivalent resistance, then you know 40 volts is applied, then you can find the current. So can you find the equivalent resistance of this circuit? That's your first job. Find the equivalent resistance of the circuit. I'll give some time. So what do you do first? Yes.
I look at the parallel.
Yeah, he looks at the parallel first and gets rid of that, right? Because that's what exactly you should do. You should find out if there's anything that can be simplified before going to the whole thing. So you go for this. 12 and 4 are in parallel, and that is something that I can get rid of and replace with one resistance. So 12 and 4 in parallel gives you what? 3. Now once you replace this with 3, so imagine you erase this and put 3 here, with just one resistance of 3. Starting from here to back there, what do you know about these resistors? They're all in series because it's like 3, then 7, then this 3, then this 3, then this 4. So just add them up because in series it's easy to add them up. So it's 3 plus 7 plus 3 plus 3 plus 4, the answer is 20. So 20 is the equivalent resistance. So R equivalent is 20 ohms, and you got 40 divided by 20 is going to be the current, which is going to be 2 amperes. Is everyone okay? Oh, it's going well.
Is it snow?
Tomorrow no school. All right.
No, this is a good one.
Is everyone okay with it so far? So you know exactly what you did?
Yes.
Now I'm going to change the circuit a little bit.
I was confused on what you did.
First, you basically you're simplifying it. So you see these two are in parallel.
Yes.
Simplify this. When you simplify these two, what do you have in place of this? 3. Right? I can erase both of those and put just the R equivalent of those two. 12 times 4 over 12 plus 4.
Okay.
So once you replace it with 3, think of you going on this journey. Do you think all these are in series or is there any other parallel?
These are all in series.
So just add them up. That will be 20. Alright? Shh.
So we just combine the middle.
It's 2.
So 3, 2, 3, all that. Find the new current. I've draw this again first of all. Draw this circuit. Draw the circuit again with the new values. And then start processing. If you look at it one way, it is just a kind of puzzle, right? Logic. Draw the circuit properly, big enough, because we'll be using that circuit a lot. Just draw that big enough and put all the numbers there, and then see if you can calculate the current. I want you to find out how much current is going there. The answer is 2 this time. Now, why? Can you tell me this? Are 7 and 3 in series?
No.
You can see them connected. Are they in series?
Yes, I thought it was.
Are they in series or no? Let me ask you another question here. Come to reality. Shelbyville Road, Frankfurt Avenue, right? Are those two roads in series? Yes or no? If you say yes, Shelbyville Road and Frankfurt Avenue are in series, if 50 cars are moving from here, the 50 cars must go through Frankfurt Avenue. True or false? False. because there's a junction there and there is a, what is the road? Lexington. So maybe the 50 cars are going from there, 10 cars going straight through Frankfurt, 40 cars going that way, right? So there's a branching. If there's a branching, you can't call them in series. Series is such a combination where the same current has to keep going, then only you can call it series. So if the same current is going from here to here, then only they're considered in series. If you have a branching, you can't have that happen. So from here, as the current goes in, it changes. So these two are not in series. So what you should do, first go tackle the innermost thing. So let me go through the whole process. 12 and 4 in parallel. This thing can be replaced with one resistance, which is 3. 3 and 3 are in series for sure, because if anything goes here, it has to come out from here. So these two are in series for sure. So simplify that, and that gets you 6. So that is 6, and that is 3, and those two are surely in parallel. Because the ends of the 6 and the ends of this 3 are connected together, so which is their parallel. So 6 times 3 over 6 plus 3 gets you 2. Now imagine you raise the whole thing and put 2 there. So then it will be 3 plus 7 plus 2 plus 4, that is 16 ohms. 32 divided by 16 gets you the current 2 amperes. So how much is the current here? Yes.
How did it go from 6 to
You know this is 3 and this is 3. So together is 6. And that 6 and this 3 are in parallel.
Oh, so you 6 divided by
So 6 times 3 over 6 plus 3. Use a parallel combination. That will be 2. And once you get this one as 2, remove this whole thing and put 2 instead. So the current has to go through this, then the 2, and then the 4. Now, let's look at it in different ways. The current is 2 amperes here. Pay attention to this one. That's also very important. If I put a voltmeter here, what will that voltmeter read? Across the 3 ohms. In other words, what's the potential difference across the 3 ohms? You know the current? How many volts? If I put a voltmeter, if I stick a voltmeter right across the 3 ohms, what should it read? Alex? If I put a voltmeter across the 3 ohms, how much should it read? Use Ohm's law. You have the current going through it, right? How much is the current going through it? 2. And the resistance is?
6.
So it will be 6 volts. So if you stick a voltmeter right across there, it will read V, which is equal to IR. You know the I is 2 amperes. You know the resistance is 3. So the potential difference that is there is 6. So out of 32, 6 volts are dropped. 32 is the total energy for the race. 6 out from here. So you consumed already 6. You get it? If I stick a voltmeter here, what will it read? The current is here is also 2 amperes, correct? 14 volts. So 6 volts dropped here. 14 volts dropped here. How much dropped so far? 20 dropped. Out of 32, 20 dropped. You still have only 12. Now let's not look at this section, because what happens over here when the current comes here is 2 amperes, but the current starts splitting up here, right? So it's kind of complicated here. So let's go finally here. What's the current here? 2 amperes. The current is 2 amperes here. So if I stick a voltmeter here, what will it read? So out of the 32 volts, 6 dropped here, 14 dropped here, 8 dropped there. So if I connect a voltmeter here across this point and this point, how much will that read? 4. You get this? So this is how we can kind of conclude one by one. So we didn't measure anything here, but we understood what should be here. So 32 there, 6, 14, 8 dropped off already, which means you are left with only 4 volts, which should be between this point and this point for sure. So this voltmeter will read 4 volts. Now, if this voltmeter reads 4 volts, what will it read here?
Can't read six.
If this voltmeter reads 4 volts, how much will it read here?
Hold up. Let me get it right.
1.3.
Well, see what is happening here. Connecting this voltmeter here, can I drag this terminal and connect it here?
No.
It's a connecting wire. You can connect it any way you want.
Yeah.
This terminal and this, they're all together. It's just one wire. So putting the voltmeter here isn't the same as putting the voltmeter here? And putting the voltmeter here isn't the same as putting the voltmeter here? So what should it read? 4.
Why does voltmeter before that? Why does that one read 4 volts?
This is 14.
No, the big one at the bottom.
Oh, okay. Because 6 volts dropped, 14 volts dropped, 8 volts dropped. So you have 28 volts dropped already. And out of 32, you only have 4 volts, which should be available here. So you know it already. And now, remember one more thing. I told you already, when resistors are connected in parallel, what should be common? The voltage. That's what it is. So what's the voltage here? 4. So what should be here? 4.
That doesn't mean 8 together.
Oh, then the current changes.
Each bulb is getting 110. So what is the potential difference across the wires coming in? It's also 110. It's going everywhere because they are all connected in parallel. So in parallel, this segment and this segment are in parallel, which means they should have the same voltage. So if the voltage from here to here is 4, it should be 4 here as well, because these are both in parallel. You see it now?
Yeah.
So if it is 4 from here to here, it should be 4 from here to here too. Yeah.
How do you calculate the current jump here?
And now you can calculate it. Now you know it's 4 volts, and that is 3. So tell me the current here. Tell me the current going here. You should know it. Yes, 1.33 amperes goes here. What is coming till here? 2. 2 is coming till here. Out of the 2 coming till here, 1.33 runs this way. So what should go this way? 0.67 runs that way. So if 0.67 is running this way, how many volts will be dropped here if I put a voltmeter there? How many volts across here? Only across this. Huh? 2 volts. 0.66666 times 3. So although we are writing 0.67, it's like 0.66666 times 3. Yes.
How do you get 2 amperes? Or no? Yeah.
That 2 ampere is going all the way till here,
Okay.
and then it splits up here. Anywhere there is a junction, then it splits. Till then it keeps going. So there was no other junction, so it went all the way till here. But now comes the decision making, split. So we understood logically, because it's 4 volts and 3, using Ohm's law, we understood 1.33. So we understand this 0.67. So 0.67 times 3 gives you 2 volts. What is the potential difference from here to here? 4, right? Out of the 4 volts, 2 are dropped here. So what should be the drop here? 2. So if I stick a voltmeter across the whole thing, it should read 2. So if I put a voltmeter here, what will it read? 2. If I put a voltmeter here, what will it read? 2. Why? Because they are both in parallel. You see how it is concluded? Yeah.
I understand how you're getting all the numbers in the voltmeter, when the current encounters resistance, like how you're saying like it drops off. Like, I understand how you get the number like mathematically, but like conceptually, what do you mean by like it drops off?
I mean, it's the energy usage.
So like, but
Like from here to here, 2 volts. What does voltage mean? How much energy per coulomb? That's basically what is potential difference.
I
So
know that like you're putting like 32 in, and you got to get 32
altogether,
the other end too,
Yeah.
right?
the total energy that you're going to spend altogether is 32. And you can see that 6 volts dropped here, 14 volts dropped here, and 8 volts dropped there. So we understand it's 4 volts across this whole combination. When it's 4 volts here, it's 4 volts across this segment and this segment because they're put in parallel.
Okay, so
And that helped you to find this current. And that helped you to discover this current.
is that what creates like the power source? So like on this end, you kind of like you're sending in like 32 volts, and the other side there's nothing coming back.
It's always like it's plus minus, it's 32, 0. Like that.
Okay.
No, not over. So we know it's 2 volts here and 2 volts here. So what's the current going in this section? It is 2 divided by 4 is 0.5. And how much is the current going there? 0.166 or 0.17. And you can see that very clearly. 0.67 is going here and 0.5 going that way, 0.17 going that way. It makes it like it's all conserved, right? And then joins back again here. What's the current here? 0.67. What's the current coming here? And then it joins up to make it 2. So it's basically it's a circuitry where you can discover. So we have discovered all the voltages across each resistor and all the currents through each resistor. We have discovered everything by using simple fundamental concepts of resistances connected in series and parallel. You get it? Now one more point. When resistors are connected in series, write this down. When resistors are connected in series, R equivalent is greater than greatest. When resistors are connected in series, R equivalent is greater than greatest. What does it mean? If you have 12 connected to 4, connected to 6, what's the equivalent resistance? How much? 22 ohms. Isn't 22 greater than the greatest of all these 3? Yes. Same way, R in parallel. R equivalent is smaller than smallest. Look at that way. What is 12 connected to 4, connected to 6? What is the equivalent resistance? Isn't 2 smaller than the smallest of these? Yeah, that's something you should understand. So, what if I connect here a wire? Look at this. This is 6. What if I connect a wire from here to here? Just a wire. How much resistance does a wire have?
None.
None. So 0 also connected in parallel. So what should be the resistance equivalent?
Negative. 0.
0. This is what we call a short circuit. You may have anything here, but the moment you connect 0, the parallel combination is supposed to drop smaller than 0, which is not possible, so 0. So a short circuit will make the resistance 0 across, so no matter what you have, doesn't matter. It shorts the entire thing.